Welcome to Beyond Static, augmenting static analysis with dynamic traces and statistical insights. So we're John and Joe. We're engineers from Zatir. We do vulnerability research and reverse engineering and development to support those goals as well. I have a background in video game hacking. That's what I did ever since I was a kid, and that's how I got into this field. And at work, I do a lot of QRC, that's quick reaction capability. So it's my normal work, but just on a compressed schedule. I also really like cats.
And I'm Joe Dussault. I also have a background in video game hacking. That's how I met John. Also like to play video games without cheating from time to time. Professionally doing RE, VR, and Cino development work. And I also like to break things, usually intentionally trying to find ways to do so, but unfortunately sometimes unintentionally, as well as my colleagues would probably say. Let's get started. So, as any reverse engineer knows, and for those who don't know, reverse engineering is a very tedious manual process. And lots of things like extreme optimization, runtime indirection, or even just the sheer size of the binary can really slow down the workflow of an engineer who wants to take a peek under the hood and understand what's going on in the binary. And we as engineers, or like anyone for that matter, really want to speed our work up. We want to get things done faster, finish our tasks quicker. Because doing so is actually quite important because it allows us to be more flexible operationally. Allows us to be better aligned to achieve more success with our work. And so the solution to this is to approach our analysis with a very specific goal in mind. Typically binaries in practice are relatively large in size, fairly large, and they'll contain a lot of things that maybe aren't necessarily relevant to our initial goal. Maybe further down the line, it will be sort of relevant to go back and take a peek at these things and try to understand them. But in order to go faster, to achieve the results we want, we need to sort of scope our analysis to make it more efficient. And so now naturally the next question is, well, how do we scope our analysis? How do we know what to look for? And this is a pretty broad question, right? Because it can depend on a lot of things. It can depend on what your goal is, what's within the binary, and what types of analysis apply. For instance, maybe you know some type of warning message or error message or something. Well, you can statically search the binary and look for strings, right? Symbols also make our lives very easy. We can see things that would have been either very tedious or maybe even have been impossible to deduce statically alone. Imports and exports to see dependencies of the binary. MMIO addresses to see where hardware resources are mapped in memory at runtime. However, by nature, static analysis limits us, right? It limits us to just what we can see statically when viewing the binary. And this may or may not be very useful depending on what your goal is. And maybe what you want to know, the behavior that is relative to your goal, might not be something you can deduce just from static analysis alone. And in these cases, you need to leverage some type of dynamic analysis, right? And so when it comes to dynamic analysis, you have things like debuggers. This will give you introspection, step through code, see what code runs at any given time. Sanitizers, detect things like memory corruption, memory leaks. Fuzzing, see what inputs cause unexpected behavior, break things, crash. And the one we'll be talking about today, which is code coverage. So for those who aren't familiar, code coverage is a very powerful capability which allows us to take the results from a dynamic analysis and layer those on top of the disassembly from our static analysis. And there's actually quite a few things that already do this and make it easier for us when we don't have something like symbols. We have Cartographer for Ghidra, Tenet for IDA-Pro, and Lighthouse, which is also for IDA and Binary Ninja. And while these tools are great and they work great in practice, it's also the case that in practice, a lot of binaries will execute code that isn't necessarily relevant to our initial goal when exporting the traces. And when this happens in these scenarios, it makes the results of your analysis very difficult to interpret. Except unless you can really finely control the conditions, it won't be very clear what's going on. And so essentially, we want to be able to utilize code coverage because it's a powerful capability and it helps our static analysis. We just want to be able to augment it to address these scenarios. So what we can do to augment it is use something called a control flow trace. And a control flow, or the difference between a control flow trace and normal code coverage is that normal code coverage is typically just a set of basic blocks that were executed, whereas control flow traces will maintain an entire record of every change made to the control flow. And if we include timestamps with this data at every control flow change, we can add even more granularity to our analysis and make it easier to see what's going on statically. And that's actually exactly what we did with our Ghidra plugin, Catalyst. And I'll hand this over to my colleague John to talk about the plugin.
So Catalyst does what Joe said. It visualizes these control flow traces. Specifically, you get some light statistical analysis in the form of a heat map and a table that you can filter each basic block by. I'm going to run through some examples really quickly of how we use Catalyst. It's going to be mostly VR centric because that's what we do. And then I'll cap it off with a demo. So this first one here is unbalanced ref counts. For those who don't know, a reference counter is a way of managing object lifetime. When you use an object, you increment the ref count, and when you no longer need it, you decrement the ref count. And when the ref count finally hits 0, the object gets freed. If you don't increment and decrement it the correct amount of times, you can have a condition where the object is still being used while it's freed, also known as a use after free. And so we can use Catalyst to look at the frequency of all of these calls to get and puts to the ref count. And that tells us if it's balanced or not. In a balanced scenario, they're all the same frequency. In this specific case, the object was never freed. We wouldn't have known that there was actually potential for a use after free unless we looked at Catalyst after the fact. Another example is when you're doing bug discovery, it's usually a good idea to look for code that's complicated. It's harder to reason about, therefore it's probably more buggy. But doing that on a compiled binary doesn't really work well because your compiler does a bunch of optimizations. Your cyclomatic complexity usually goes through the roof when you're looking at compiled code. And so we measure the entropy of all of the different targets taken from a basic block, and we use that to supplement our idea of what complex code really is or isn't. This is an example from Catalyst, just some screenshots of low entropy code versus high entropy code. It's the same code, just different conditions when the binary was executing led to different routes being taken through each path. Another small example, we have this next blocks feature, which is helpful when you're looking at like C code. You don't have V tables or anything like that, but you have indirect jumps or calls. You can just, because we have the record of all of the branches that were taken, we can easily, from any basic block, go to all of the other blocks, even though we don't have like an offset in our code. So for the demo, I'm going to use Mongoose, which is an embedded web server. It's similar, if you've ever opened up like a router or something, you'll usually see like a small HTTP server, and that is usually what serves your web panel so that you can actually configure the router and whatnot. That's just the stand-in for something like that. Can you guys see it all right? Okay. So what I'm doing here is I'm running this test.sh script. Essentially, all it's doing is wrapping the web server in a Dynamo Rio trace client. And it can output a format that our Ghidra plugin Catalyst is able to understand. I'm going to log in on the device dashboard here. And then the functionality that we care about is on this page. So it's the upload firmware button. So what we're going to do is we're going to find this specific upload firmware route in the binary just using Catalyst. So I'm going to cat out this script here. This is just some JavaScript to spam the route associated with this functionality. I just gave the source of the page to ChatGPT, and it gave me the script back. So we ran it, we get a bunch of errors, and that's because we don't really know what the backend actually expects. But we don't really care about that. We just care that we actually exercise the code path in the binary. Whether it's an error or not, doesn't really matter. So I'm going to go into Ghidra here, and I'm going to first import the binary and analyze it. And then after that, I'm going to load the trace with Catalyst, which takes a little while, so I'm going to speed it up a bit, but it's kind of slow.
Can you talk about the input files your Catalyst script takes? You mentioned, was it Dynamo traces? What was that?
Yeah, so Dynamo Rio is just a tracing engine for a couple of different architectures, and we're using that as a way to essentially just count all of the basic blocks that are being executed. The actual format of the trace is just like a simple CBOR file that has all of the modules and like their memory addresses so that we know which blocks belong to what map memory region, and the basic blocks themselves.
Are there any other file formats you accept?
No.
Like, let's say I want to use this one Hydra for a embedded processor, some other processor that Dynamo doesn't support.
Yeah, you would just have to write a script that can output it into that format.
So we've experimented with other instrumentation engines that do more as well. I'll get into that a bit later.
All right, so it's loaded in here. We can see the table view is populated now. And if I go and I select the thread that we traced here on the left, we can see that the heat map gets populated. And this heat map, you can see features in the map that correspond to things that we did while we were tracing the program, right? So at the very beginning, you have these blips of activity that you don't see again anywhere else. That's going to be your initial setup, right? Creating sockets, allocating structures in memory to track incoming connections, stuff like that. Then there's a pause. The next blip of activity is likely the login page being served to us, and then yet another pause, and then we have 3 more blips of activity. This is us logging in and then getting more web pages served back to us. And then a really long pause after that, you get this hotspot, the hottest spot on the graph, which is actually what we're looking for. That's the script that we ran and spammed the web server with. So I'm going to focus in specifically on that region. And then here in the table view, now that I've focused on that region, I can apply some filters to the data set. So I want to look at all the code that's internal to just this binary, because we trace all of the basic blocks. That means stuff that's in shared libraries that might not actually be in this program database. So I want to make sure that our external setting here is set to false. And I also want to make sure that we're looking at all of the basic blocks that exist exclusively within this region that we selected. And then lastly, I'm going to filter on the number of times that each basic block gets executed. And this is taken right from our script. So in this case, ChatGPT decided on 313 times for some reason, and we're going to filter explicitly for that. And here you see we've cut down our set dramatically. I think there's something like 7 functions in here as opposed to hundreds. And I'm going to filter these now by the function so they're grouped together. If I click on the first one and scroll down, we get confirmation on line 26 that this is the handler for uploading firmware to the device.
So now we've seen practical utility with the plugin. It's important to note that there's still some open problems and work to do. One thing that's true about this is that we are doing all of the analysis within the plugin itself, which is not the way to go for a few reasons. One issue we ran into when doing that is when you have a large trace size, maybe that's gigabytes in size. It'll use up a multiple of your RAM. I think we had like an 8 gigabyte trace that used up like 40-something gigabytes of RAM, which is obviously not sustainable. Also, Java will throw random errors at some point, like maximum array size exceeded. And so the way to avoid all of this mess is to essentially take the analysis portion of this and implement it in native code. And then when we do that, we can stream the results from that native code into our Ghidra plugin using some sort of IPC mechanism. And doing so will not only avoid all of that mess of doing it in Java, but it'll also allow us to do real-time trace analysis. And also just speed things up in general. One thing we hadn't implemented yet is with readjusting values when you filter in the set of listings. So with values like your entropy or your frequency, these by nature are relative values. They are relative to the other basic blocks. So when you filter for specific listings that are relevant to the behavior you care about, you want to readjust these values relative to just that local filtered set. As it currently stands, even after you filter, they stay relevant or relative to the global set of all traces, even the ones that we don't necessarily care about at that moment. And we're also lacking frequency based on shared frequency, or analysis based on shared frequencies. So when you use the tool, you'll notice that a lot of basic blocks in the listing will share a lot of the same frequencies. And we want to add a capability to the plugin in order to recognize these shared frequencies and be able to group basic blocks under the shared frequencies to allow for better filtering for the user. Click on a shared frequency and see all the listings that are associated with that shared frequency. And so that's all we have for today. Thank you guys for coming to our talk.
So we have about 5 minutes if there's questions.
Questions?
Great demo. Can I get your doc file for your terminal?
Yeah, sure.
That cursor was crazy.
Yeah. This is cool. When I do like tracing, I really like to do differential stuff. Like I love to take a trace, take another one, and subtract one from the other. Or only get the intersection, right? But it seems like with this, you could do differential like in between, say from this timestamp, remove everything that was executed here in the initialization phase. I only want the stuff special to the handling of the handlers. Have you played around with that at all?
So
easy
the
to add with how you guys have it set up?
yeah, the question was there are a lot of differential capabilities in the plugin. Have we experimented with using them? And the answer is yes. That is the driving force behind the entire plugin, is just being able to diff at whatever section that we want.
And I'll also add that sort of getting the format of that trace is sort of left open, right? So you can use any type of like time stamping that you see fit, like CPU, clock cycle or something like that, to give as much or as little granularity as you'd like in your traces. Yep.
Question is, are we publicly releasing this? Yes, probably next month.
Yep. And we will be including the Dynamo Rio trace extractor that we use in this demonstration as well.
So it sounds like for this, you're mostly looking at inside one run of a binary. Do you have any capabilities for like across 2 different runs of binaries or multiple different trace files?
The question was, in the demo, we were looking at one run of the binary, and do we have any capabilities to look at multiple runs of the binary at once? And the answer is yes. You can look at as many trace sets as you can load into the program database, and you can bisect them however you see fit with the filters. Yes?
Can you talk, so I'm obviously not familiar with the Dynamo file format. Is it similar to like WinBag's timeless debugging, like where it's a full like timeless trace, or is it like specifically just the basic blocks? Like I guess I'm just not familiar with Dynamo.
So the question was what the trace format actually is like. So Dynamo Rio is just a client. The trace file format that we have is custom, and it's just CBOR. So it's like JSON, but binary, right? So it takes up a lot less space.
Well, I meant more like what data do you need to record? Like obviously you need to record every basic block, but like for the initial input to your script, do you need every entire execution trace? Like do you need registers? Do you need memory changes? Like do you need?
Right. So we don't need all of that data. Essentially, all we record is we have another thread that is acting as a timekeeper. And so we get timestamps from that, and we get the address of each basic block that's executed, and a list of all of the modules that were loaded in the binary at the time.
And we had experimented with other instrumentation frameworks. We tried Frida. Frida was good. It just didn't give us the granularity that we wanted with our traces, so we used Dynamo Rio. I also had experimented with Intel Pin and gave us similar results to Dynamo Rio, but the way the actual trace extracted is left open. And it would be a cool sort of follow-on project or something, or more work to do to sort of set up a toolkit or a suite of trace extraction that you could use.
All right, awesome. Can everyone give a big round of applause for